Okay, hello class. I'm so sorry to be posting lectures on a snow day. However, with Monday's class canceled, the only way I can maintain that canceled is by posting today's material as a set of videos. So I'll go through it. I had a pile of homework examples planned for today. If this was an in-class lecture, I'd probably post solutions. Since I'm sitting here at the iPad, I'll probably make up solutions, but I'll clearly label those as homework, so you don't have to go through those if you prefer not to. So last day, we covered circular motion of a charged particle in a magnetic field. We discussed the application of velocity selectors and a mass spectrometer, and we talked about magnetic force on current carrying wires. So that's the equation to find it. Here's the right-hand rule. Our pre-class question will take us through that. I will post the solutions there, but I won't go through that one. It's a pretty straightforward problem. Try and keep the notes organized. I will scan these when I get back on campus and post those along with the rest of your lecture notes. So the example we'll do today to finish off our section about F equals IL cross B. Let's make it a little bit fancy. Let's take a metal bar. It's got a mass of 750 grams. It has a length of 50 centimeters, and we attach it to two light metal springs. The resistance of the springs and the bar combined is 6.82 ohms. The springs are connected to a battery, and the system is oriented vertically so that the bar is hanging down. The system is set in a 3 Tesla magnetic field which points out of the page. And why don't we draw what that field would look like? So a vector coming towards us, it's like we're looking at the tip of an arrow. So we see those dots pointing out towards us. So this is our magnetic field, B. We'll label that B. When the switch is open, the springs are extended past their equilibrium length by 2.5 centimeters. What happens when we close the switch? And once we close the switch, the circuit is connected, current's allowed to flow. There'll be a current carrying bar here set in a magnetic field. We know it'll feel a magnetic force. Okay, let's deal with the switch open part first. So let's deal with this part first. If the switch is open, there is no current, which means there is no magnetic force. Let's draw a free body diagram for our bar. So I'll draw the bar here, put in my coordinate system x and y. If we ask what's happening with the forces on the bar, we know that the earth pulls it down. That's the force due to gravity, or the weight force. We know that springs will pull it back towards equilibrium. In this case, the springs pull it up. There are two springs, so there are two spring forces. One on the left and one on the right. We'll apply our Newton's second law. Sum of the forces on the bar in the y direction is the bar's mass times the acceleration in the y direction. The forces we have are the spring force up. We remember that spring's force is given by kx, where k is the spring constant. We've got the weight down minus mg, and we've got the spring force up plus kx equals mass times acceleration, but the acceleration is 0 because it's not moving. Kx plus kx, that's 2kx, minus mg to the other side equals mg. If we look at this expression, x is the extension of the springs, m is the mass of the bar. We can find the spring constant of our springs. K equals mg divided by kx. Oops, sorry. K equals mg divided by 2x. M is 0.75 kilograms. G is 9.81 meters per second squared. 2 times the extension, got to put that in meters. And we get our spring constant K equals 147.15 newtons per meter. Okay, we weren't asked for K. However, we are going to move on to closing the switch, running the current through, and figuring out what's happening there. We'll still have spring forces, so it's going to be good to know K so that we can calculate what those spring forces are. Okay, let's move on to step 2 with the switch closed. With our switch closed, we get current running. So let's do a picture and let's see what we know about that. So switch closed. Do a quick sketch. There's my springs attached to my bar. There's my battery allowed to run. I know that current is going to flow out of the battery, comes out of the positive terminal. It's going to flow through here. My bar is still set in my magnetic field, which points out of the page. The current is flowing through the circuit, comes down through this spring, goes through the bar this way, and up through this spring here. Okay, not the best springs ever, but hopefully you get the picture of what that should look like. So with the switch closed, we do get a current flow. So let's say what that current is. We know that V equals I times R. So I equals V divided by R. The potential of the battery was 9 volts. The combined resistance of the whole thing was 6.82 ohms. So our current flowing through our system is 9 over 6.82 equals 1.32 amps. And the direction of our current flow is shown in our picture here. So now we know that there's a current flowing through the bar. The bar is in a magnetic field. It's going to experience a magnetic force. Let's draw a new free body diagram and let's see how everything comes into play. So I'm going to redraw my bar, straight line across. I'm going to put in the 3 forces I know right off the top. Is that my two spring forces hold it up, Fs, Fs. I know the earth pulls it down. That's the force due to gravity. We draw that right at the middle. What about the magnetic force? Here's where we use our right hand rule. Thumb goes with the current. Index finger is the magnetic field. Extended middle finger is the magnetic force. So that points down in my picture. Same direction as gravity. There is my FB. Okay, so what are we going to do with this? Why don't we figure out an expression for our magnetic force and then we'll come to our Newton's laws. So I know that my magnetic force has a magnitude of I times L times B times the sine of the angle between L and B. So I've got my current I, that's 1.32 amps, times the length of my bar. The length of my bar is 0.500 meters, times the magnetic field it's sitting in, that's 3 Teslas. And so I know my L, my B, and the angle between L and B, this is to the right, this is out of the page, that's 90 degrees, equals ILB. All right, when I apply my Newton's second law, the net force on the bar in the y direction is mass times acceleration in the y. Acceleration in the y is 0, so the net force is 0. I've got a spring force up, magnetic force down, gravity force down, spring force up. All has to sum to 0. My spring force is K times X, magnetic force is minus ILB, gravity is mg, spring force is Kx, equals 0. Okay, let's remember what we were asked for. What is the extension of the springs with the switch closed? Ultimately, we are trying to find x, so let's do a little bit of algebra. I'll put my two kx's together, take my ILB and my mg to the other side. So my x is I times L times B plus m times g divided by 2 times k. Here's where we see that it's pretty useful that we found k in our last step. So let's go through the math. I is the current that we found, 1.32 amps. L is the length of our bar, 0.500 meters. B is the magnetic field in which it sits, 3 Teslas. plus m times g. M was 0.75 kilograms. G is 9.81 meters per second squared. Divide that by twice the spring constant, which was 147.15 newtons per meter. And we find that the extension of each of the two springs is 0.0317 meters, or 3.17 centimeters. Okay, there's that example done. The next slide in the notes, if you've looked at them, has got another circuit. It's got a switch. We've got some resistors and a battery. When we connect the switch, we're going to get some current flow. Current flow through this bar means it's going to feel a magnetic force. We're asked to find the acceleration, so we need to use Newton's law. Sum of the forces equals ma. We'll include the magnetic force, and we'll try and sort this out. I'm not going to work through this as part of class. I will work through it and post it as a homework video, however.